All right, in lecture 29, we're going to finish up chapter 24, and that'll be all of the material for exam 3. So we're first going to talk about syn dihydroxylation of alkenes and alkynes using osmium tetroxide, so OSO4, and potassium permanganate, KMNO4. And so syn means the same side, and dihydroxylation, so dihydroxy means we're adding two OH groups. We're going to add an OH group to this carbon and an OH to the group to this carbon, and they're going to be pointing in the same direction. So we use osmium tetroxide. We also need hydrogen peroxide in the reaction, so H2O2. Gives us a mixture of these two products. And so the osmium can approach the alkene from the back face behind the board or from the front face in front of the board and then add two OH groups. And so we get a mixture of it being towards us and away from us. The other reagent we can use is potassium permanganate. And so KMNO4. This also requires potassium hydroxide, and it accomplishes the exact same thing. And so again, it can approach the double bond from either the back face behind the board or the front face in front of the board, putting OH groups on each of those sides. And so you should think about what's the relationship between these compounds, and so revisit the meso, diastereomer, and enantiomer definitions from the spring and determine the relationship between these molecules. Notice that this double bond is trans, and we get addition to the same side. This double bond is cis, and we get addition to the same side. And so the geometry of the double bond doesn't matter, but we have the groups pointing in the same direction. Alright, so I said we can do it with alkenes, we can do it with alkynes. I'm not going to talk about the mechanism, and so I'm not going to hold you accountable for that. Just know that osmium tetroxide and hydrogen peroxide do the syn dihydroxylation. Potassium permanganate and KOH can do the same thing. Remember that osmium tetroxide is probably your better reagent to use because it's selective for alkenes. Potassium permanganate, we've seen it quite a bit this semester, and it can do a variety of reactions. It is required for alkynes to do this reaction though. And so if an alkyne is your only functional group in your molecule, then you could do this kind of reaction. There's two pi bonds here, so it can react twice, where the alkene only has one pi bond, it can only react once. And so I'm not going to draw this out properly, but so here there's 1, 2, 3, 4 carbons, and we add two OHs to this carbon and two OHs to this carbon. And so it ends up kind of being like that. And then if we want to draw that out properly, we got to do our zigzag structure. And it looks like this. So remember back from chapter 17, I believe, whenever we have a hydrate like this, so we have two OHs coming off of the same carbon, these would prefer to lose water and become the ketone. And so we end up losing two H2Os, and we get a ketone on both of these carbons. And so that would be your product from the oxidation of an alkyne using potassium permanganate and potassium hydroxide. All right, so we're going to move on to 24.8. We're going to talk about the oxidative cleavage of alkenes. And so I'm not going to talk about alkynes, so you don't need to know that. And the book lists a couple other conditions that can be used to accomplish this. I think ozonolysis is the best way to do this. And so I'm only going to focus on ozonolysis, and that's all that you need to know in terms of the exam. So what we do is we take an alkene and we treat it with ozone, which is O3. And this ozone, O3, adds to our double bond and gives us a 5-membered ring, which we call an ozonide. I'm not going to go through the mechanism, and I'm not going to require you to. But once we make that ozonide, that is explosive and highly reactive. And so we got to treat that ozonide with some type of other reagent to get the final outcome of our reaction. So one thing that we can use is dimethyl sulfide, so CH3SCH3. And this is what we call a reducing agent, and so we're going to end up with aldehyde products. And I'm actually going to add one more carbon here so that we can see better see the outcome of the reaction. All right, so when we do this kind of reaction, we use a reducing agent, we get aldehydes out. And what we do is we essentially just pull that double bond apart and put oxygens on each side. And so I've drawn this line through the middle. And so we just want to redraw this right here and put an oxygen on it. Like that. And then we want to do the same thing on the other side. So we look at it here and then put an oxygen on there. And those would be our two products. And so notice, like what I said, if we use a reducing agent like dimethyl sulfide, we get aldehydes as our product. If we take the same alkene and we treat it with ozone, then we're going to get the same ozonide intermediate. But if we treat it with an oxidizing agent instead of a reducing agent, these become carboxylic acids, because once the aldehyde's formed, the hydrogen peroxide is able to further oxidize it to the carboxylic acid. So we use hydrogen peroxide, it's an oxidizing agent, and so again, we do exactly like what we did before. We're going to look at this side of the alkene right there. Just pull it apart, put an oxygen. And then since we're using hydrogen peroxide, this H coming off here becomes an OH. And so that is a carboxylic acid. Same thing on the other side. In this case, we had an H coming off of here. In this case, we're going to have an OH. And so we end up with carboxylic acids. All right, so let's take a look at this reaction here. Notice that this is a cyclohexene molecule, so I have an alkene right here. And we just learned a type of reaction that makes these type of compounds, and that's the Diels-Alder reaction. The Diels-Alder reaction gives us a cyclohexene, which has a single double bond in there. We can take that product and then treat it with, and put it into an ozonolysis reaction, and further convert those rings to other molecules. And so again, when we do ozonolysis, we make the ozonide on the alkene, and then here I have my reducing agent, and so I'm going to get out an aldehyde. So again, we just chop this right down the middle. Notice that this side is tri-substituted, so it's the first time we've seen that. There is no hydrogen coming off of either side of the alkene, and so our only possibility is to get a ketone. So now that we're ripping this apart, we really just want to pull the ring out into a straight chain, and our oxygen is going to be here. And so let's count our carbons all the way around. 1, 2, 3, 4, 5, 6, 7. So we're going to have a 7 carbon chain. All right, and then if we start here, carbon 1, carbon 2 is going to have the ketone. And then if we go all the way around to 3, 4, 5, 6, 7, that means on our 7th carbon that we're going to have the aldehyde. So 1, 2, 3, 4, 5, 6, 7, and we have our aldehyde. And so again, make sure you're counting your carbons and stuff so you don't have too many or not enough. And again, when you have a tri-substitute double bond, a ketone is your only outcome no matter whether you use a reducing agent or oxidizing agent. And in the ring, it rips it apart to give us a straight chain. All right, so we move on to 24.9, talk about the Diels-Alder reaction in syntheses. And so when we're trying to go 3, 4, 5 synthetic steps, the Diels-Alder reaction can be really useful. So if you see a 6-membered ring and it's not a benzene ring or an aromatic ring, think about a Diels-Alder reaction and see if that can get you to the right answer. And so let's go through the Diels-Alder reaction again. And so I have my diene here, and both of my groups coming off are pointing in towards each other. And so they're going to be on the same side of the ring. And then we'll talk about which way this points in just a second. So Diels-Alder always gives a 6-membered ring. That's a cyclohexene. And so that double bond ends up being between these two carbons where the diene is. So then we have this point right here coming out towards us. And then remember that this group is going to like to be away from this so that there's not any steric hindrance. And then if we redraw this molecule, so this is a top view, if we draw it from a side view, then it looks kind of like this. And so we want our ester group pointing away from this up here. And since this is into the bigger ring here in the bottom, the 6-membered ring, instead of the 5-membered ring up here, we call this the endo product, which is usually the major product in the Diels-Alder reaction. Also notice that we have an alkene right here. So we always make a cyclohexene. And alkenes can participate in lots of reactions. And so remember the Organic Chemistry 2 playbook that I posted earlier in the semester. It has a page on there like this where we learned a ton of reactions that alkenes can do in the spring. So when you're going through the exam and the project and stuff, don't forget about the playbook that I made. It summarizes every single reaction we learned in the spring. All right, let's run through a couple examples and then we'll be done with this chapter and the material for exam 3. All right, so let's say we want to convert this molecule to this molecule here, and we can use any reagents possible. And so we already have the right amount of carbons. We have 6 carbons here, 6 carbons here, and so we don't need to add any other carbons. We just need to use different reagents. So what I'm thinking is somehow we need to get this carbon into the ring to make the 6-membered ring. We just learned a reaction that allows us to open up a ring that has an alkene in it. So maybe we can open this up and then close it back together to make the 6-membered ring. So we will use ozonolysis. And then we want to think about whether we want a carboxylic acid or an aldehyde. And so remember, the aldehyde, once it's formed, gets converted to the carboxylic acid. So I'm just going to draw out the aldehyde, and we'll think about if that's the best product to obtain. So again, we just cut right here through the middle, pull those open. So we have 1, 2, 3, 4, 5, 6 carbons total. And if we start here, we go 1, 2. So on the second carbon, we're going to have our ketone. 3, 4, 5, 6. So off the 6th carbon, we're going to have our aldehyde. So 1, 2, 3, 4, 5, 6. There's our aldehyde. And so should we use a reducing agent to keep it at the aldehyde, or use an oxidizing agent to take it to the carboxylic acid? Well, now I'm thinking, okay, we got to get to the 6-membered ring. And so to do that, I need this carbon, which was this carbon, to somehow attach to this carbon. And we know how to do that. This would be an intramolecular aldol reaction. And so we know intramolecular aldol reactions, we could either deprotonate here, here, or here. And if we deprotonate here, that's 1, 2, 3, 4 membered rings, so we can't do that. deprotonate here, that's a 1, 2, 3, 4 membered ring, so we can't do that. If we deprotonate here, that's a 1, 2, 3, 4, 5, 6 membered ring, which would help get us to here. Also, the aldol condensation results in an alpha beta unsaturated ketone, and so I think we need the aldehyde, not the carboxylic acid. And so we need the reducing agent so that we keep it at the aldehyde. Now to do the aldol condensation, that's just some base and some heat, and so it'll deprotonate here, attack here, we'll lose water to get to our alpha beta unsaturated ketone. So again, if you have a smaller ring, need to get to a bigger ring, think about ozonolysis to open that ring up and then reclose it via a different reaction. Let's take a look at one last example. And so this is a really complex molecule, and it is an intermediate on the way to a natural product that was synthesized by E.J. Corey many years ago. And so we want to draw the product of the Diels-Alder reaction. We know that the Diels-Alder reaction involves a diene and a dienophile. Usually the diene is electron rich, so it has alkyl groups attached to it, or hydroxy groups or something like that. And then the dienophile is an alkene that's attached to an electron withdrawing group. So if we look around this molecule, we see that we have an alkene here, and an alkene here. These alkenes are next to each other, and so this will be our diene, have our 4 pi electrons. This will be our dienophile, and so it has the 2 pi electrons. Remember, the Diels-Alder is a 4 plus 2 cycloaddition. And this is attached to 2 electron withdrawing groups, making it fairly reactive. And so remember, Diels-Alder reactions always form 6-membered rings with an alkene in between these 2 carbons. And so we're going to end up having a 6-membered ring up here. And so we want to redraw this whole carbon skeleton and then draw our 6-membered ring up here. All right, so I got the whole carbon skeleton part drawn here. That does not change. And so remember, now it's these 2 carbons up here that become part of a 6-membered ring with this carbon and these 2 carbons here. And so there's our 6-membered ring. And then remember, we get an alkene in between the diene. All right, so think about your carbons here. This is 1, 2, 3, 4, 5, 6. And so 1, 2, 3, 4, 5, 6. And so we look around those. Off of 5, we go down towards this carbonyl. We go over to this oxygen. And then that oxygen is still bound to this carbon. Then up here on carbon 6, we have a methyl group coming off. And we also have an aldehyde coming off. We're not going to worry about stereochemistry in this outcome, because we're going to get a mixture of the methyl group pointing in one direction and the aldehyde pointing in the other direction. And so, even though this looks like a complicated molecule, you just have to identify the functional groups that will react with each other, and then take your time to draw out the carbon skeleton, and you'll get to the right product.